Okay, hello everyone. We are going to go ahead and get started. Welcome to the Velocity Software ZVM training class. My name is Sam Weigman and I will be your host this week as we go through modules 1 through 3. Before we go over the rules, I would like to introduce the founder of Velocity Software, Barton Robinson.
Thank you, Sam. I want to just welcome everybody to our very first ZVM education program. My name is Barton Robinson. I'm founder of Velocity Software. Velocity was created to provide ZVM management facilities. Having been involved with the ZVM platform for almost 50 years, I believe VM is by far the most efficient and mature virtualization platform there is. After 60 years of IBM integrating the VM platform and the ZVM mainframe technology, ZVM performs better and is much more resilient than any other of the newer offerings. The challenge today I hear from executives worldwide is the lack of ZVM skills and the lack of people that have those skills, and that those skills are more relevant to their decisions than the significantly better technology provided by ZVM. And having had many friends and seeing many other skilled professionals retire from the business, taking their skills with them, there is a real need to rebuild those skills worldwide, which is the point of this program. So Velocity Software has been providing informal training for our new hires for quite a while, but the greater worldwide need, we have worked to formalize that program to be a useful program for all, at no charge, for the good of the community. So we hope to continue this program for as long as there is a need and demand. Enjoy the show. Back to you, Sam. Thank you very much.
All right, awesome. So up first, we have a couple of rules to go over. First, all sessions are being recorded. Recordings can be found on our website in the near future. Second, everyone will remain muted. Any questions should be typed into the chat box or emailed to questions@velocitysoftware.com. I have that up on the screen. We have people monitoring the chat to help answer your questions. Third, some of our sessions will involve a built-in WebEx tool called Slido. You don't need to download anything for this, it is built in. This is for multiple choice quiz questions. You must participate in the quiz questions in order to receive your class certificate. All right, up first, we have Intro to System Z with Rick Barlow. Rick has over 40 years of ZVM experience and has been with Velocity for 7 years. Ask him about hardware if you have plenty of time. Go ahead, Rick.
Can everybody see that now?
Yep, you are good to go.
All right. So the introduction to System Z. Why do we start here? The main reason is that we believe that understanding the fundamentals of the machine can make everyone better at programming, at understanding what you're looking at when you're trying to measure, do capacity planning, any of the things related to using the machine. I think can be better understood if you have a little bit of knowledge about the fundamentals, what's behind it. So let's get started here. Here is a basic agenda. I'll talk a lot about what's in a mainframe, all of the parts, because those things make mainframes different than any other computing platform you may be familiar with. We'll talk a little bit about what you have to do to set up a machine to be able to run workload on it, and that's in the area of the I/O configuration program, IOCP, and defining LPARs. I won't go into a ton of depth on those, but I'll introduce those concepts. I will talk a little bit about the hardware management console, and that's how anyone might interact with a mainframe and do the hardware functions that you have to do for your machine. Then we'll move on a little bit further into virtualization. So we're going up the hardware stack. So you start out at the machine, you move up to virtualization, and then we'll finish with just a little bit of time on the IBM Z operating systems, and there are many of them. Let me first, before we go too far, differentiate what I would call a mainframe from what you often hear people refer to as a mainframe. So, a mainframe is the computing complex that we all use to run any number of operating systems. And you will often hear people in the ZOS space refer to ZOS as the mainframe. Well, ZOS is just one of the operating systems that can run on that mainframe. So if you hear me talk about mainframe, I'm going to be talking about the entire infrastructure system, and it may be running ZOS, it may be running ZVM or KVM or Linux or VSEN, any of the operating systems that might be on our machines. So that's just probably important as a fundamental piece of information. So an introduction, what makes IBM Z different from other hardware platforms that you may be a little bit familiar with? First of all, uh, because it is almost everything is owned by IBM, produced by IBM, you have innovation all the way across the software stack. And this is a graphic that someone shared with me some time ago. Uh, so those arrows across the bottom came from another presenter, but I have actually updated some of the pictures above it. So you look at the semiconductor technology, IBM designs the chips, and they design the hardware packaging, so the microprocessor design and the entire system. And we'll talk quite a bit more about the system design. They have control of the operating systems, many of the tools, most of the tools, I suppose. Well, that's not true so much anymore. With the inclusion of Linux, there are a lot of tools from a lot of different people that run here, and even containers in the ZOS environment. You have tools like Python and all of the open source tools that can run on um, every platform that's available today. And then you have that whole set of optimized middleware, and most of those that are listed here are actually IBM middleware tools. Uh, anyway, so moving on, it's not just a computer. I guess I should have maybe bolded that, underscored it. It's a set of computers. So if you look at a mainframe, you will find not just a set of processors or cores, you may hear them referred to as, uh, but you will also find all of these other components that are really computers in and of themselves. Most of the cards have processors on them. And then in the case of a mainframe, you also have a lot of outboard hardware involved, switching equipment and um, IO subsystems. For example, a disk subsystem is really not so much disks anymore as is a set of disks and a couple of computers in front of it that make it pretend to be a disk like the mainframe is accustomed to. And I'll talk more about that in a little bit. But you can see here on this block diagram, this is actually a Z17 ME1, and at the uh, at the bottom in the middle, you'll see the water cooling units. This system is actually water cooled, but it's not water cooled necessarily by water from your facility. It's water cooled with a self-contained air conditioning unit. That's one option. You could have it plumbed to water in your building. Uh, up anyway, yes, you could have it plumbed. But then you'll see at the top two important pieces of hardware that are included in here. There are a pair of gigabit Ethernet switches, and there are a pair of units called hardware management appliances. And the hardware management appliances are actually the tools that let you interact with the machine, and the support element function on there monitors all of the other components. And I'll talk more about those in a few minutes. Then all of those other silver boxes on both sides in this particular drawing are IO connections. And so those would be I/O drawers where you can connect to external subsystems. This machine has nothing plugged in, so it's kind of hard to tell, but those could be disk connections, those could be network connections. If you're running ZOS, you probably have uh, coupling connections between multiple machines so that you can have the Sysplex up and running. So one of the things I really love to share with people, if you don't know about it, IBM has this interactive product tour catalog. And that's a live link in the presentation charts when you download it. I encourage you to go look there. On that website, you can click on any one of these machines and you can uh, have a 3D model of your mainframe. So whatever particular uh, model you have in your site, right now there are Z15s, 16s, and 17s available on that website. And we happen to have a Z15 TO2, that's why it's on my picture. The Z17 ME1 up until yesterday was the current model of IBM, and they announced the Z17 ME2 and MR2 and Linux 1 Rockhopper 5, I think is the current name for the Linux 1 only machine. So you'll see that one coming soon to the demo page, I'm sure. I doubt it's there yet since it was just announced yesterday, but it will be coming. So this is IBM's definition of what's a mainframe. Data servers that are designed to process up to 1 trillion web transactions daily with the highest levels of security and reliability. The key thing is that they are designed for handling large amounts of data in a highly secure environment and to be able to be agile in processing all those transactions. If you can imagine, the majority of the banks in the world, especially I should say the majority of the large banks in the world use mainframes, and a vast majority of the data that is contained on IT systems around the world is hosted primarily in mainframes. So what makes them unique? A lot of it is the packaging. I talked a little bit already about processor drawers and I/O drawers. If you look in the picture to the right here, uh, there are up to four CPC drawers, and those are the processors in a Z17. And then all of those other silver boxes that I talked about are all of the I/O connection points on the box. And this can have up to 15 I/O drawers. Each drawer contains up to 16 I/O connections. And then the RCA is the modular air conditioning units that I talked about. On the single frame IBM Z, you can have up to 2 CPC drawers. Most smaller shops have just one. The reason you might want to have 2 CPC drawers is if you have multiple drawers, you can facilitate non-disruptive changes. And what that means is the IBM Z is the only machine I know of in the world where you can replace components while the machine is up and running. I have personally been a part of running a production workload on an IBM Z, taking a drawer out of a machine, replacing one or more components. I've seen memory replaced. In fact, I've actually had a chance to help the hardware technicians replace memory in a Z10 that was running production workload. So if you have multiple drawers, you can actually do concurrent repairs. There's very few parts in an IBM mainframe that cannot be replaced while it's running. Most of the I/O cards can be replaced, and the components in the CPC drawer can even be replaced. It's a pretty phenomenal piece of hardware. So this is a Z17 processor drawer photo and some description of what's involved. This machine has 5 nanometer electron or wire traces in the chip. So if you can imagine a trace of electrical conducting elements on a piece of silicon that's only 5 nanometers wide, and that's smaller than a human hair. That's how the wires are put on the chips. There's 8 cores per CP, and there's a drawing of that here in a few minutes. And there's 1 I/O engine on each of the processor chips, and there can be up to 4 processing unit dual chip modules, and I'll talk some more about the dual chip module in a few minutes too. The dual chip modules on this picture would be where these rubber hoses are. They're actually down in the bottom. This isn't the greatest picture of that, but I'll expand that in a few minutes. All of these green cards are the memory, and this machine can have up to 4 terabytes of memory in it if it was fully loaded. What else is important about this? Another feature of IBM Z that is unique is the memory in these machines is made of these DDIMMs, dynamic DIMMs, or I don't remember the acronym, but the point of these memory DIMMs is they're not just standard like you would find in any other platform. These actually are arrays of memory, not unlike you would have a RAID array in disks. These have the same kind of a concept in memory, and I'll talk a little bit more about that in a few minutes as well. At the front of this drawer are all of the connections to the rest of the machine. With the drawer out, you don't see any of the cables on it, but you would have up to 12 slots here for connecting to the I/O drawers and to the other coupling links if you need them. So they would be plugged in here at this bottom section of the front of the drawer. Oh, skipped one, sorry. This actually happens to be a Z15 processor drawer. So this was from an older, you'll see here in 2 generations of the machine, one of the things I wanted to point out is on the Z15 was a 14 nanometer, and now we're down to 5. The next generation of machines, they expect to be 3 nanometer electron traces. There's over 20 miles of wire in a Z17 processor chip. So the reason I kept this chart in here is you can see here in this particular picture, these are the 4 single chip modules on a Z15. Now we're in dual chip modules on a Z17. The 15 had this storage control chip at the upper part here. That's the interaction with all of the main memory. In the Z17, we no longer have a storage control chip. That function has been moved onto the main dual chip modules. So with each generation, IBM does its best to improve the latency between the processors, the cores themselves, and all the other components. And so that was another move from having this separate storage control module to moving that function onto the chip, moves it all closer, which makes the pipelines for processing data and instructions faster. This is a block diagram of a Z17 chip, and it has more details of all of the things that are included. So here is the built-in AI processor. Oh, my apologies. I didn't mean to go anywhere. How did I do that? the built-in AI processor. And on this Z17, there can also be a set of Spire AI accelerator cards in an I/O drawer. If you have basic integrated accelerator needs, the AI chip or the AI function built into the chip will handle that. If you need lots of AI, then you go to the Spire cards in a drawer. I mentioned that we no longer have the storage control module, and this chip, the DPU, this DPU function of the chip is the I/O engine, and this is what interacts with all of the I/O functions in the Z17, and I'll talk more about those. These cores, you'll see there's actually 8 cores on this module, or on this chip. There's also lots of level 1 cache for each core. There's these level 2 caches, and what's another thing that's unique about the Z17 is these level 2 caches can be shared by other cores. So if this cache is not busy with the core that's closest, it can be used by other cores. And you'll see here there's actually 2 level 2 caches. If we didn't have this DPU engine on here, it's pretty obvious to see there could have been 2 more cores on this chip, but this particular design using the DPU on the chip meant there's 2 less cores. Here we then have 72 megabytes of additional level 2 cache that is available for these other cores to use. And one of the things the microcode on the machine will do is help move that function of those caches to the cores that need them the most. Very unique design. This is a similar drawing of the Z15, and I leave it here because you can look at the comparison between the cores on the chip, the amount of wire. Here's that 24 miles of wires on this chip. On the older chip, there were only, I thought the miles was on here. Oh, it's not on this particular chart. But you can see the number of transistors. So Z15 had 9.2 billion transistors on the chip. The Z17 has 31 billion transistors on the chip. It's just an amazing high density silicon chip. You also can see here that this chip had up to 12 cores on it, where the new one only has up to 8. Anyway, so what apologize, get my thought back together here. With each core on a chip, it is characterized by the function that it'll be used for. The firmware does that characterization. When you configure a machine, you purchase a certain amount of capacity on the chips. They could be personalized as a CP, that's a general purpose. ZOS uses that. An ICF is for coupling. Once again, it's a ZOS only function. An IFL, for those of us who love ZVM and Linux, that's what the majority of our engines are. And if you get a Linux 1 machine, it's going to be all IFLs. For certain ZOS workloads, having a zip processor is also useful. And there is a non-user function called the integrated firmware processor. The integrated firmware processor is used, like its just name says, to take care of the firmware on the machine. So it's basically a core that is doing work that is not your work. It's not the customer work, but it is the work that helps support the machine. Likewise, there's system assist processors. Those are part of handling the I/O operations. And then the Z has another function that is not common to any other computer platform that I know of, and that is a spare. And a spare is on the chip in case one of the used cores fails. And the machine can dynamically move that workload to a different core and continue to run. So for example, let's say you have 2 chips on your box, which would be the minimum. So 2 of those 8-core chips means you have 16 cores available. One or more of those, one will be an integrated firmware processor, at least one will be a system assist processor. But let's say you license 7 IFLs, the rest of those cores are available as spares. So if one of the used IFLs cores fails, the microcode will automatically move it to a different core while the machine is running. So here is just for comparison, this was a single chip module in the Z15 having up to 12 cores. In the Z17, we have dual chip modules. Each one of these Z17 chips has those 8 cores, 1 DPU, 1 AI accelerator, all within one of these silver blocks. So if you, these are roughly the same size chip carriers, and the chips are very similar in size. You can find that on the previous charts where the all the statistics were. So you can see now we've nearly doubled the density within that same footprint. I should say we've got 2 chips in the same footprint. It's way more than double the capacity. That was not stated very well. So moving on, let's talk a bit about memory. I mentioned this earlier. I couldn't find a chart of the Z17 version of this, so this is the Z15 version of the RAIM, redundant array of independent memory, that works a lot like RAID does in disk. All it really means is there's more memory really in there that the machine can dynamically spare if there are parity errors in the memory. So I'm not a technical wizard in terms of the memory capability here. Uh, Somebody might read this powerful 90 90-bit, 64-bit Reed Solomon code. I have no idea what that means. It's under ECC, which is error correction code. So I know what error correction code is. The readout Solomon code is some sort of algorithm that it uses to figure out when there are failures. DRAM failure, it can automatically mark them. It'll be called for replacement on the 3rd failure. There are lane failures, and this all means a lot to people who are memory designers. But just suffice it to say that we now in a Z have a way where the machine is dynamically taking care of the memory and making sure that your workload doesn't fail because of a memory error. Memory errors are not that common. However, this machine has the capability of working around them and moving them, making a spare useful to us. So one of the things that does is if you're in, this was once again a Z15 chart, because I can find those. So what you really have, if this is the amount of memory you're paying for, let's say that's 1 terabyte, there's automatically a certain amount of additional memory in the machine that handles that sparing capability. And you don't pay for that, which is kind of nice. And there is a piece of memory, we won't talk too much more about this, called the hardware system area. It's 160 gigabytes on a Z15. So there's 160 gigabytes of memory that are a piece of this totally installed memory that you don't have anything you don't ever use. That is used for saving the IO configuration and other system functions. So HSA on this particular machine, this yellow block, was 160 gigabytes. I am not sure what the size is on a Z17. I will look for that piece of information and maybe add it later. So the next thing that's different in mainframe than any other platform is all of the I/O is outboard of the machine. So if you pick up your PC and you look at uh, the internal design, you'll find a processor, multiple cores, most likely. Typical PCs these days have 4 or 8 cores. Um, there's also some sort of a storage media, whether that's a disk or a solid state device or an NVMe. So you have some memory in there, and then you have a display. Now, we used to have CD-ROMs or DVD drives. They've quit putting those in PCs. One thing that the PC has to do is that core, that set of cores has to take care of all of the memory refresh. That's done separately in the Z by one of those extra processors on the chip. So the CPU cores in a mainframe are used entirely for compute, and other CPUs are used for memory refresh, as opposed to your PC has to manage both of those on the cores. And I/O in the mainframe is all outboard of the machine, so you won't find any storage devices, an SSD or an NVMe. Well, that's not true, because now you can have an NVMe on a Z17, or a Linux 1 version anyway. Same basic hardware, 2 labels, 2 different functions. The Linux version can have an NVMe in the frame, very fast storage. I won't have time to talk more about that. So anyway, in the I/O subsystem, there's a number of functions that you will hear referred to. The channel subsystem is the set of I/O cards that are available to the machine. They direct the flow between the I/O devices and the main storage. So that's the main storage being the memory in the box. I'll have to update this chart because everything in the mainframe world, we're moving to talk about memory now to be consistent with every other platform. We've always called it storage, and that gets confusing when you talk about storage devices like disks or storage devices like tapes compared to the memory in the machine. So in the future, you will hear that referred to as main memory. Um, the channel subsystem relieves instruction processors of communicating with the I/O devices. That's what I was just referring to in the comparison between, for example, your PC and a mainframe. The channel subsystem is handling all that work. It allows the I/O operations to continue independently within instruction processors. So there, 2 things are happening with every clock. At least 2 things are happening with every clock cycle. Channel subsystems handling I/O, and CPUs are doing real processing work. The channel subsystem handles path management. So many of the I/O devices in a mainframe have multiple paths to them. You will find some of that in the PC world, but not very much of it. Well, anyway, it also communicates with external devices through channels. The next piece you have on top of the channel subsystem is you have a channel or a channel path. That's a PCIe path going from the processor drawer to an I/O drawer to be able to talk to some sort of peripheral devices. What other info here is really important? Oh, hardware resides in the PCIe I/O drawer. That's what I just said. You also have a kind of a connection in a mainframe that is a little bit unique. We have the ability to have hypersockets, and that is a channel that's implemented in the mainframe firmware for network connectivity between logical partitions. So for example, in most platforms, you would have some sort of a Ethernet connection, probably a 10 or 25 gigabit connection these days, to go out of your box, talk to some place else in your network. In a mainframe, if you have multiple LPARs running different workloads, you can have a hypersocket, which is an implementation not too different from that Ethernet connection, but it never leaves the box. So it operates at memory speeds instead of at light speeds that go out on the network. So hypersocket can be a very fast connection. One place that would be very useful is if you have a database, large Oracle, large DB2, running in a ZOS partition uh, or a Linux partition, for example. Then you could have a middleware or a web front end running in another partition, communicate between those two by hypersocket. Now you have all of that data that never has to leave the box. And so you get high speed communication between your data backend and your network front end. The next piece of the IO subsystem is a subchannel. And all that means is that on a given channel, you can have multiple devices connected. And the most common piece of that puzzle is in disk storage. And when you have disk storage, you'll have one channel connected to a whole subsystem with a whole string of disk devices behind it. So that's what a subchannel is. A control unit is a little harder to understand. In the early days of mainframes, there was a device called a control unit, and it was a separate device. So you would have a channel connected by cables to a control unit, and then that control unit connected to whatever storage devices were behind it by some more cables. Well, the control unit physically doesn't exist anymore, but it is a logical piece of the IO subsystem. And it's what translates the channel commands to whatever the devices on the end understand. And then you have the IO devices. That's the last piece. You have each IO device is connected to only one control unit. And those control units can be accessed via one or more channels. And that'll become a little clearer, I think, when we talk about disk, because that's the place you see it the most. So this is a slightly older drawing of Z15 IO infrastructure. And you'll see at the top here, you have memory, you have the processing units, and you had that storage control chip that I mentioned that doesn't exist in the Z17 model. Then you had a number of PCIe fan-out connections to IO drawers. So the green boxes are IO drawers. And then those have PCIe buses that have the actual IO cards plugged in. So in this class of machine, you also have these red boxes, which I'm going to come back to in a minute. Those are application-specific integrated circuits, and those were IBM Z proprietary pieces of these IO cards. And in the Z17, those go away, which is a very good thing because that allows for more industry standard IO cards. And I'm going to show you some more of those here in just a moment. So this was a comparison drawing that I found, which was very helpful. So if you think of a processor drawer where you had CPU with PCIe, then you had this switch, and then here's those IBM application-specific integrated circuits, the red boxes on the prior chart, and the IO firmware, and then you had this industry standard adapter. Now with the Z17, most of the IO cards, there's a couple of exceptions, but most of the IO cards now do not require these IBM specific pieces in the middle. You have just an IO card, plugs directly into the PCIe bus, and industry standard on the end. One of the things that facilitates is in the same physical space, I can now have a four-port card, where in the old one there was only room for two because so much of the real estate was taken up by these IBM specific interface cards. And all of that function that used to run on those two red blocks has now been moved to that data processing unit function on the Z17 chip. So we took all of these smarts that used to be out here in the channel subsystem, we pulled them all in here and put them in the DPU, allowing for delivery of new function with each new processor chip. Used to be, it took a while to update all of the IO cards with newer capabilities because every card had its own software built in. Now that's all moved into the DPU, so it's easier with each generation of the processor chip to improve the functions. So that's what this is all about. Very, very cool function of the Z17. Here's another view of that. So this is an older card on the, for example, the Z15 and 16. The industry standard part of the card is very similar. You can see it out here in the pink shaded area. But we had this whole bunch of stuff, real estate on the card eaten up by this IBM Z-specific ASIC and all of the support for that. So think of this as another computer, which it essentially is. It had to have its own memory and other support chips on the card. So now in the new function cards, we get rid of all that IBM ASIC, still have to have some of the support stuff. There is a redrive. So this is a PCI bus on the outside. Then there's a PCI bus within the card. This particular card doesn't show it, but you could actually have double this industry PCIe card now. So for example, on a disk card, you'll have 4 ports here instead of just 2. On the older cards, it was limited to 2 because of the real estate of the ASIC. The other thing that's happened with each generation of machine, the interfaces between the processor chips and the PCIe I/O cards, the speed has doubled multiple times. So the Z13 is a machine that came out in, it would be about 9 years ago, I think. At that time, it was a 16 gigabyte per second bus. Now they're up to 32 gigabyte per second. So we've doubled the speed in this last 9 years. And you can see previous generations of machine way back to 2 gigabits. And so that bandwidth between the IO drawers and the PCIe cards, it just continues to go up. So I had the channel subsystem descriptions a couple charts ago. This is just a block diagram showing similar, the same words, just in terms of the building blocks as a stack. You have the IBM Z, so that's the whole processor complex. You have the partitions, you have subchannels, channel subsystem, and channels. So those are just the building blocks of the IO subsystem. Here's a couple more examples of the card. This is a current Ficon Express 32 card that you might find on a Z17. You'll see it has 4 ports. Those are industry standard LX or SX ports. There's the inclusion here of the fiber, and you'll have one of those 3 kinds of fiber on that you're using in your data center. You'll find that most mainframe shops use LX cables. I don't know where that tradition came from. It's always been that way. You'll find in most of your distributed, they're using SX or the multi-mode fibers. I can't explain it. I just know that's the way it is. So here you have an image of a card. Here's the PCIe bus that connects to the I/O drawer. This is, I don't actually know what the black part is covering, but out here on the left side, you see the industry standard type components and 4 industry standard fiber connection ports. It's just the view from the inside as opposed to the outside. And as I mentioned before, these cards are hot pluggable. So if the machine is running and you end up with a failure on these ports, as long as there is a redundant connection, you could have the machine disable this card, pull it out of the drawer, put in a new card, and re-enable it and reconnect. Now with a 4-port card, as you might imagine, that might make it more difficult. A 2-port card, there's more likelihood you had an extra card with for redundancy. 4-port card, you may or may not. So trade-offs within the machine. And this is a pre Z17 Ficon Express 16S. So this was the 32 gigabyte connections, and this was a 16 gigabyte. And here's this isn't actually a photo of it, but you can see the IBM ASICs on this card, and they take up a lot of space there in the middle. Same fiber connections, whether it was long range or short range. But from the outside, then you see this is a photo and there are only 2 ports on it because of this configuration. One of the biggest changes with the Z17 class of machines has been this Network Express card. They were brand new on the Z17 a year ago. This is a high-speed 10 or 25 gigabit Ethernet card, but it also can do not only gigabit Ethernet, it can also do Rocky function, which was a separate card on previous generations of the machine. Now you can actually do both functions over the same card. And I'm just in the process of learning about this as we try to ramp up and get a new Z17 running here. So I can't explain a lot more about that whole Rocky function. Linux is doing all of their networking over that function. So if you're running a Linux LPAR, you probably know a lot more about this than I do already. And this is an older OSA Express. This happens to be a 1000 base T card. We have cards like this in our Z15. Here again is the bus connector out here. Here's all the ASIC processing stuff, and then you have the industry standard parts of the card over here. So just comparisons between the 2 types of layouts. Moving on then, another change in the Z17 architecture is the I/O drawers. They're all 16 slots now, and they have only ports out the back of the machine. Previous generations of the machine, I'll just go here temporarily. In the Z15 and 16, you had 32 slot I/O drawers, and there were cards in both the front and the back. Made for cabling really interesting because you always had to be sure which side of the machine your cables had to go to, which made your cabling more complex. It made the I/O drawers more compact, and you could put more things in fewer drawers. But these were also the 2-port only cards. Lots of differences. Just suffice it to say, all the cabling's now in the rear of the machine, and most data centers will love that. And this is an actual photo of a card, so you can actually see the different card types. These are all 2-port cards, so my guess is that these are more network cards. I don't know. I can't read the labels. They're too small for my old eyes. But you will also find when you're going to cable in this center section, there is a location indication. It says LG 01 or LG 11. And those are the card locations in the machine. They're used not only for the hardware people to know where to plug cables, but they are also the card locations so that when the microcode of the machine is interacting with you, for example, if this card fails, it will tell you go to the card in location LG 11 or 12, and that is the card that needs to be replaced. So those are all location indicators. The middle, these two larger blocks, are where the connections to the CPU drawers go in. Those are the PCIe bus connectors. Another thing that is unique in the IBM Z is built-in cryptography. There is actually a cryptography assist function built onto the processor chips. This happens to be a model of a picture of a Z15 chip once again. So you could have these chips in the drawer, but then if you need a lot of complex cryptography, so if you're doing the advanced cryptography functions, then you will have a crypto express card in the NIA drawer. For example, there's a card down in this drawer. Those cards are managed by an external trusted key entry workstation. So all of the keys that you need are fed into them by this workstation that is also protected. So all of this you get into with card readers and smart cards and distribution of responsibility where you have one person's going to take care of the keys, somebody else is going to take care of the access to them. This card, when you have a Crypto Express card built into the machine, this gray box is a tamper-proof device. If anyone would take this card out of the machine and attempt to do something with the cryptography module, it automatically will remove the keys that are built into it. So nobody can steal your keys out of the hardware. And this TKE is the only other place they exist, and these are always kept in a very secure location. This has all the advanced cryptography functions. I thought I had a list. Yeah, here's a list of some of those more advanced cryptography functions. If you understand all these, you maybe have a certification behind your name like CSSP, because those are I don't understand all the algorithms. And now you have the elliptic algorithms. So this is a Crypto Express 5 card. The current generation, I believe, is Crypto Express 7 on the Z17. So highly advanced, high security cryptography that's built into our machines. Somewhere in between those two is the CPACF function on the chip. This is the same two block diagrams of a Z15 and a Z17, but built into every one of these cores is this CPACF, so crypto processing accelerator function card. Anything else here? Nope, we got it. Nothing else really to say about that. I apologize. I thought there was maybe more. You can read the details when at your leisure. For the business value, this is the business description. You get into these certification levels, and I'm going to come back to that in just a minute. Whether you need a TKE or not, CPACF. So if you want an accelerator, or you need a coprocessor, or you need an EP11 coprocessor, these are the things you'll need, and it helps you determine when you need the Crypto Express card, as opposed to just working off of the accelerator function that's built onto the chip. And I talk about all that. This is a slightly older chart from the IBM Z13 days. But IBM routinely goes through security certifications of the machine. I wish I could find this chart concisely for the new machine. I'm sure someone's got one somewhere. But this talks about those certification levels. For example, here's ZOS had at the time an EAL 4+ certification level, and this is what it took, the software stack that it takes in order to get that. And if you want common criteria EAL 5+, you also have to have RACF at these levels or higher, ZOS 1.10, etc. So this is the set of software requirements to meet up to these certification levels: EAL 4+, 5+, FIPS 140-2. Similarly, ZVM has one like that, and Linux does the same thing. So here's at the time, the SUSE 11 was certified at EAL 4+, Red Hat EL 6.2, that's Enterprise Linux 6.2. So there are charts like this, and I could find all the individual information, but I couldn't find one where somebody had gathered it all together, and I didn't do that myself. Here's ZVM version 6.1, so that's pretty old, because we're at version 7.4 and 7.5 will be out soon. And certification happens usually, in general, every other release of most of these operating systems. The process is long and expensive, so they don't go through it every time. Oh, and here, the other thing that's important here, the Crypto Express 5S card was also designed for that same level of certification. So those things all came out about the same time. So moving on then, let's talk a little bit about disk subsystems. These all are external to the mainframe. You'll hear lots of different phrases used for disk. So this is actually an old spinning 3390 Model 9. These are actually disk platters. This was the last generation of real spinning disk. They had gone from early, I think the first discs were 7 or 8 inches. They had gone up to 10 inches. This is actually, I think they'd gone to 12 inches, I should say. These are 10-inch platters. So if you can imagine, those are fairly heavy. Metal platters with recording media on the top and the bottom. This black device is a set of read-write heads that move in and out to be able to read these disks. That doesn't happen in the current disks. If you still have spinning disks in your disk subsystem, they're typically 3.5 inch or maybe 2.5 inch, depending on the particular model of your disk subsystem. Most subsystems now have gone to solid state, with perhaps some spinning disks as a lower tier for lower cost retention in there. But you'll hear lots of terms. You'll hear DASD. Most mainframe people talk about DASD, and that's direct access storage device. You'll hear people talk about CKD, or ECKD really is the right term. Count key data has to do with the way it's formatted on the disk. Today's disks are all emulated extended count key data, which is what the E is in ECKD. They're often called FICON disk because that's the way the mainframe interacts with them. Let's see, okay, so all of that is done by channel command words or channel programs that are written by the software and sent down the channel tell these disk subsystems to do something, whether it's go seek and find some data and return it up the channel. So that is DASD, so typical mainframe disk. I mentioned this already. Today, it's cabinets full of less expensive SCSI SSDs or disks. The disks themselves are all formatted in fixed block sizes, which is why most of the open systems architectures use FBA or fixed block architecture. Some of the trade-offs are that the DASD formats or ECKD include built-in multipath processing and a lot of statistical information that gives you details of how the performance is working to those. Until recently, FBA, the open source side of this, didn't have the same level of measurement capabilities. That is improving since most of our Linux on mainframe workloads include open source disk or FBA, fixed block. Those are the terms you'll hear on the other side. It's becoming more important for us as people who measure our performance and capacity on mainframes to get more performance information from the disk subsystem. For example, it's pretty important to know how long it takes to send out a request for data and get the answer back. If it's measured only at the processor, you lose a lot of the information about where are the other delays, queuing in the control units and in the disk subsystems and in the channel subsystems. So you'll see more of that data showing up in the relatively near future. FICON, the architecture allows only one active I/O per subchannel or per device. We have a function in the mainframe environment called hyperparallel access volumes. And in simple layman's terms, that just means we've defined an extra subchannel that is an alias for a single disk. So we could have up to 16, I think it's up to 32 hyperparallel access volumes for a group of disk. And the cool thing about hyperparallel access volumes is they are dynamically managed between the operating systems and the storage subsystems. So the parallel access volume may belong on one subchannel for a given period of time when it's really busy. And if that device becomes less busy and another one nearby becomes more busy, the hyperparallel access volumes can be moved around dynamically. And if you have a good measurement tool, you will find those statistics telling you how well you're using your hyperparallel access volumes. And I mentioned here at the bottom, SCSI is getting better at measuring, and we'll see that show up. So now I'd like to move on a little further into how you define all this stuff to your mainframe processor. The basic program is called the Input-Output Configuration Program, or IOCP for short. It provides all the I/O subsystem information necessary to tell the hardware what's out on the end of your channels. No matter what kind of mainframe you're using today, you're going to have something that creates an IOCP that then becomes compiled into an IOCDS or IO configuration dataset. The IO configuration dataset is a location in the mainframe that the microcode can access, and it provides the information then that is loaded into that HSA I mentioned earlier, hardware system area, that lets the microcode know how to interact with your IO subsystem. It uses assembler-like macro instructions. So for anybody who didn't think assembler was still important, you might want to know a little bit. They're simple macros. the machine only knows some basic information about how many devices are out there and how big the data transfer blocks are. So there's only a few pieces of information the machine needs. The software may need more. And then you'll find, for example, in ZOS and ZVM, you have a tool called the Hardware Configuration Definition, or HCD. And ZOS requires you have HCD because ZOS also requires a lot more information about devices for building its control blocks. ZVM being more of a hardware architecture simulator. That's the word I was trying to find. Doesn't need much more than the hardware does. So it's a simpler definition process, and ZVM will dynamically accept whatever the hardware presents to it, which is very nice because we don't have to use HCD on VM. You can choose to use it, and if you have multiple machines and those multiple machines share IO subsystems, for example, a DASD subsystem could be shared among multiple mainframe processors, then I would recommend that you consider using HCD because you get a single picture of all of the connections to a given subsystem. And that can be very useful when you're trying to manage your overall IO environment. I was involved in an environment where we had over 65,000 devices defined to a set of LPARs. We shared a lot more resources. You'll find in most shops today that they tend to segregate at the hardware level. There's good reasons from a security standpoint. Since ZVM is capable of running all of these workloads as virtual machines, sometimes it's useful to have those devices shared so a ZVM system can see them in order to provide a test environment where you can gain access to devices. Now, your production data, you don't want to share that with your test systems. That's a bad practice, but there are a lot of places where, for example, your program libraries, sharing those is not a bad idea because then you can test them in multiple environments. That's about all I had to say about that. So here's one example of defining an IOCP, some IOCP macros. So up here in the top right, you'll see a picture of what is this? An HMC definition of one partition. It's too small here to see. This happens to be a Linux partition. So in the IOCP macro, this is what that definition would look like. There's a resource macro. That's the key to it is resource, and some list of partitions. They're in channel subsystem. We mentioned that earlier, channel subsystem 0. Modern machines can have up to 5 channel subsystems. And this is a list of 3 Linux LPARs that are a part of that channel subsystem. Now, you can have up to 16 LPARs in each channel subsystem. That's why you would need more than, it must be 6, because you can have 208 partitions on a modern machine. So must be actually 6. Anyway, this is the graphical interface on the HMC. This is how we got it there, by defining it in an IOCP macro. Then you have some chipid. A chipid represents one of these ports, usually, on an IO card. So I think this was probably an older disk IO card. It only has 2 ports, but we're defining a path. So, and we're going to put it in channel subsystem 0. We're going to call it chipid 06. It's going to be shared among those LPARs. Now we could not make it not shared. So this is where you could segregate it, and we could say this path is only available to one of these LPARs. In this case, I chose to share it between the LPARs. And it's physical channel ID 162. So there's a hardware physical channel ID that goes with every physical location in the box. And then you give it a logical channel path ID of, in this case, 06. Then we have a control unit. This is actually a picture of an old disk control unit. When there were still spinning 3390 disks, this was a 3990. Today, you would have a unit of, for example, 2107 would be a common disk subsystem unit today, but you still have devices defined as 3390s, which is interesting. But so we have on this control unit, we defined it on that, we gave it a number of 60. It's on channel paths 6, 7, 8, and 9. So in this case, I really would have 3 more chiplet definitions. And what that means is I've defined 4 I/O ports that plug into this control unit. So 6, 7, 8, and 9. I've defined it with 128 disk devices behind it. CU add a 0. Let's not go there. That gets into how the control unit and the devices talk. That's a detail that's probably not important for this discussion, but they are unit type of, this case was a 3990. And then we have I/O devices. And so we've given it a set of devices. We've given them a starting address of 1600. There's 128 of them, matches the number I said the control unit can talk to. It's on control unit 60. So this number refers to this control unit. This control unit refers to one or more chipids. So there's 06, points back to this 06. And that's how these macros are all related. Status detect is just a disk parameter you have to put in. There's a IOCP book that has all the rules and regulations of any other parameters that might be required on one of these macros. And this was for a 3390. So what I've done here is I've defined a logical set of 3390s. These are old hardware pictures. I should have probably put a modern disk subsystem next to it. It looks a lot different than these do, but so there's just how to assemble the building blocks. That's really all I'm going to tell you about IOCP today. That's a whole in-depth discussion that is better for another topic. If that becomes your responsibility, that's another place we'll have to provide some training eventually, probably. FICON directors is just another name for a switch. FICON director is there were 2 major companies that provided them, Brocade and can't remember the name of the other one, who did standalone FICON directors. Today, a lot of your data switches, Cisco switches, et cetera, can do both data and Ethernet. So you may not have a separate set of devices, or you may. Keeping the FICON and fiber channel connections for disk separate from the others helps to segregate the capacity of your switching units. So switches are not cheap. And if you have lots of Ethernet connections, for example, lots of blade centers, you're eating up a lot of switch ports. And you may not want your disk to be interacting on the same devices. That is another discussion for another day. So the switches can provide dynamic connections between IBM Z processor complexes and control units. So for example, if you have several IBM Z processors in your environment and you have several disk subsystems, you will most likely have a FICON director or a switch involved in that so that you don't have to have as many ports on either end. So let's say you have 4 ports from each of your processors. You have 4 processors. You're going to have 16 connections. You want those 16 to all go to that same set of disk subsystems. So using a switch, then you don't have to have 64 switches or 64 ports, I mean, on your disk subsystems. You still only have to have 16, and the switching units allow those all to be shared. One place you have to have a FICON director is if you're going to use end-port virtualization. End-port virtualization on a disk subsystem allows you to hardware isolate access from a given Linux image, for example, to the storage subsystem and a LUN on the storage subsystem. That is a complex puzzle. The Z has built-in firmware to help you with the end-port virtualization, but the definitions become more complex when you have to use that on FCP channels. The switches also enable growth. What you can do when you have a switch is you could install a new disk subsystem and migrate to it without having to do all the recabling at the time of the cutover to a new disk subsystem. So it's good for migrations like that. And it enables the resource sharing, like I mentioned. If you have multiple processors, one disk subsystem, then you can share if you have switches built in. And in the IOCP, then there is another set of parameters you will add when there are switch ports involved. Once again, that's advanced IOCP and more than we want to cover today. So the next thing you want to be able to do, especially as a system programmer who's going to interact with your Z machine, is you need to talk to it. And that's done via a function called the hardware management console. On the older machines, there was a device built into the machine called a support element. And the support element then had an external hardware management console. In some of the versions of the machine, it looked a little bit like this. This is a newer machine, so this is what's called a KMM, or keyboard monitor mouse, and all this is a 1U device where this monitor can fold down, slide into the box, and so you have a keyboard, a monitor, and a mouse on this that then can interact with your machine. The support element was a dedicated function, and the hardware management console was external to the device. Hardware management console is simply a web interface that can connect to your support elements to manage your machines. On the Z16 and later, actually Z15 was the first place you could get a hardware management appliance. It was optional on the Z15. Since the 16, it is the only way. Hardware management appliance has 2 functions on it. It has a hardware management console built in, and it has a virtual support element. So on the same unit, looks much like this, it's running both functions on each device. There are 2 of these in every Z machine that are redundant. One is always active and one is in standby mode. If you have either have to load new firmware or there's a problem, the machine will automatically move from one to the other. So you have redundant support elements or hardware management appliances. The KMM I managed, this manages all of your power up and power down. So fun piece of information, maybe fun, might scare you too, is if you have one of a Z machine and you have remote access to it via web, which you should have access via web, but it should be well protected behind a firewall, etc. All of those things, you should have the right level of security on your hardware management console, so only the right people have the right authority to do the right functions. But technically, from anywhere in the world, you can log into your hardware management console and then you can access your support element, and you can power down the machine from anywhere in the world, which is really, like I said, it's both interesting and a little bit scary that you could do that, but you don't give that authority to anybody except the people who should have it. Typically, that's a operator-only function and granted only when they need it, kinds of things for those who are very highly security-minded. And the HMC has all of that security built into it. It has all of the appropriate TLS kinds of things. And most data centers keep those devices under lock and key in a data center and behind a firewall. So not hard to do. These devices, the hardware management appliance, holds all the system firmware. So when you get your machine, there's basic power on self-test kinds of stuff, but everything else is loaded from the hard drives in these hardware management appliances into all of the components of the machine. So remember, we talked about the fact that on the in the processor drawer, the chips need to have their firmware loaded. Every one of these I/O cards, the data, go back to the chip, the data processing unit needs to have all of those I/O functions loaded into it. Every one of these I/O cards in this, you can see a few of them here on the side, has to have firmware loaded into it. The backup copies are all stored here on the hardware management appliance. That's why there's 2 hardware management appliances and backup hard drives within the hardware management appliances. So you have all of that redundancy. But that is how the machine can help self-manage all of the hardware. It monitors and it will phone home, assuming you provided access. It is can be made allowed to call to the IBM Support Center and report any incidents that occur. I think that's all. Services system, yeah, 2 fully redundant appliances. It communicates through the CPC support element. So those functions you'll find now on the modern HMAs, I think there's just 4 Ethernet connections, 2 for the HMC function and 2 for the support element function. So you have redundant network connections as well. The tasks performed to the HMC result in commands being sent to 1 or more SEs. By that I mean, well, it's coming here. One HMC can control up to 100 support elements. So if you have 50 mainframes with 2 support elements each, a single HMC can manage that entire environment. It can get confusing. I'll show you the interface in a minute. If you had all of that stuff on a single set of displays, you might not want to do that. So you might segregate your machines based on like production versus test versus AT, those kinds of things. One support element can be controlled by up to 32 HMCs. So you could have 32 points of control. Once again, that would be a very complex puzzle to manage. It'd be like a whole network of just the HMCs and support elements. Keep it to a minimum. That's my recommendation. You only really need one hardware management and HMC location to control a handful of machines. So don't use any more than you need to for your sanity, I guess is the right way to say it. This is a hardware management console display. You can see over here on the left side of this, this must be an older because it says ensemble management. Ensemble was a function IBM tried for a little while. I should find a newer picture. That's the only thing I just noticed is on here that doesn't make much sense. Normally, you will see the the machine name. So this AT Sense 1 is a processor name that somebody's given it. Normally, we'll find those directly under the system management heading on this frame. This one, like I said, this is an older, this must be a Z13 class machine. It doesn't matter. Everything else on this looks pretty much the same. So wasn't really important. And I didn't look at the software level on this. Yeah, this is 2.13. That was a Z13. So I need a newer picture, but everything else is the same. You have this is the list of LPARs. This is their current state. If they're operating, not activated. Not operating means it was activated on the machine, but there's no operating system running. So you, in this case, you don't see an operating system over here. When you have an operating system up and running, it'll tell you the name of the operating system. It'll tell you what it is. These happen to be ZOSs. Here's a VM system. And then you have the software level out here, which is kind of nice. You get a picture all at once from one place. And then the functions in the bottom window are how you would interact. So the management functions, recovery, if it goes down, change management has to do that's where you're finding all the definitions for the LPARs, et cetera. So this is an HMC example. Once again, there's a whole another session on managing systems with an HMC that would be a lot of fun to do. Here is how you would define a new image profile. So when you bring up a machine and you have this new LPAR that you put in your IOCP, this is, what is this, UOSP0B, which you can see down here where it's not activated. Even though I put it in the IOCP, it has a placeholder. Then I've got to go through and define the image profile. And this is where you would do that. You would select what operating system type it is, assign processors to it, enable performance controls, all of these functions. You just basically go through this wizard and it steps you right through making those definitions. It takes about 6 screens minimum to get a functional LPAR, but then you can use the other ones. For example, you don't need to go into the crypto functions if you are not going to use the advanced crypto capabilities. So you don't need to go through every one of the pieces. And then once it's defined, here is the graphical user interface. So if we went to this HMC and we picked this USP04 LPAR that is the 4th one down, I could go down there to change management, or excuse me, operational customization, and I could select the operating system profile, and I would get this basic display. And here, then I could choose what's running in it. This one was an example of a ZVM LPAR. You can actually, one of the things you can do in a ZVM LPAR is you can use any of the processor types, which is CPs and IFLs and zips, and well, that's all. There aren't any more. If you go ESA 390 only, that's a ZOS LPAR. ESA 390 TPF, that's for a ZTPF LPAR. Imagine that. Coupling facility, if you're going to do a coupling facility on a machine, so you can have 2 ZOSs talk to each other, 2 or more ZOSs, a coupling facility is a special type of LPAR. So you have those in the list. And a Linux only, you can imagine, will only let you run Linux in the LPAR. Moving from there, we're going to go into a little bit of discussion about virtualization. On a modern mainframe, there is no basic mode, and basic mode was a way that a single operating system could manage or could control an entire mainframe system. That hasn't existed now for several generations of the machine. I think it's mostly because the machines just got so big that the operating systems none of them could really utilize at that level. I could be wrong about that, but anyway, so every machine runs in under the Processor Resource System Manager, or PRISM. Back up a step, I got ahead of myself. Virtualization on a mainframe happens in the hardware. There's a special instruction in the microcode called Start Interpretive Execution, or SI. And SI is how virtualization on a mainframe dispatches workload. And there are two levels of SI. One is used by PRISM, which is the microcode version of virtualization, and the other is usable by ZVM. So PRISM is the foundational firmware on a mainframe that acts as the hardware level hypervisor. So it is allowed to carve up the real resources into subsets of resources. Now, one of the main differences between PRISM and doing ZVM virtualization is PRISM can only carve up the resources into chunks that all add up to the total. It can't make up any new parts. It can't pretend there's anything there that's not really there. PRISM will carve the resources into multiple logical partitions, or LPARs. For those of us who are really old, PRISM is actually a descendant of VM in around the mid 1980s. And if you can put the machine in the right mode, you can still see some things under PRISM that looks very much like they do in ZVM CMS. I actually saw a machine run in that mode one time. Anyway, so logical partitions are created by PRISM, or if you like to say Processor Resource Systems Manager, you're unusual. Most people just call it PRISM. Then ZVM. One of the big differences is that ZVM, while the machine can handle a maximum of 208 LPARs on a Z17, ZVM can create thousands of virtual images. There's a famous test from the early 2000s where someone ran 39,000 virtual machines. Now, they weren't really doing much work, but the fact is ZVM can manage at that level. And what ZVM can do that PRISM cannot do is it can overcommit resources. And by that, if I have let's say I have 4 terabytes of memory on my machine, I can actually define virtual machines that add up to much, much more than that. I can have a dozen or 100 4 terabyte virtual machines. Now, you have to be able to support that in terms of the paging subsystem and other resources that are needed to manage that. But it will let you overcommit at those kinds of levels. Now, it's not recommended. For a production workload, you don't want to overcommit anywhere near that. For a test workload, you might be able to overcommit that kind of level. And that's one of the things that you need to know your workload and have a good set of capacity management and performance tools. The other thing ZVM has is CMS, the interactive part of the ZVM environment. Another piece that at one time could run standalone on a machine, but hasn't been able to for a long time. CMS is where you as a system programmer would interact with your machine. And the great thing about it is has wonderful tools for automation and measurement and capacity planning. It may be the most robust in the world. You'll find on ZOS systems large amounts of performance tools, often consuming a large amount of available resources. I've seen many ZOS systems running where the performance tools consume 10% or more of the available capacity. That seems like a lot to us. So you don't really want your performance tools to consume that much of your workload. The CMS environment, the tools there have very low overhead and very high capabilities. And some of the later sessions we'll talk about some of the tools that we use in the ZVM world and that provide some of those functions. So this is a block diagram of virtualization on a mainframe. They called it an IBM Z host. Just should replace that word with mainframe. You'll see at the bottom there's some amount of real resources in the light blue, processors, memory, and I/O. Prism can carve those into multiple logical partitions, and here we have depicted 5. Then in those partitions, you might run an operating system by itself, ZOS, ZTPF, etc. You can run Linux on Z in an LPAR if that's the way you need to run it. But then you can also run ZVM in one of those LPARs. And this is where the 2 levels of PSI come into place, because Prism is using one to dispatch the LPARs. ZVM then can use the second one to dispatch the virtual machines that run on top of it. Here we have depicted a VSE. For those who know VSE, there's no longer a ZVSE, it's now VSEN by 21st century, or lots of Linuxes. The other thing you can do here is you can run any of these operating systems. Anything that could run in an LPAR can run in a ZVM virtual machine. You wouldn't run production workloads in a virtual machine because of the reduced capacity of running second level like that. But you can certainly do a lot of testing, and many shops use ZVM as the host, virtualization host then for doing testing of all of these workloads, whether it's Linux, ZOS, TPF, VSE, etc. And you can run KVM in an LPAR. I think that's a little bit of a deception because KVM itself isn't an operating system. It's a piece of a Linux. So I don't know if that's the way I would depict it, but whoever drew this picture, that's the way they did. And then down here at the bottom, there's a nice, really old 370/168 picture. So that's the processor resource I picked for this picture. And you have disk, tape, print, and you might have a card reader. Today's computers, even though they don't have real card readers anymore, ZVM takes advantage of a virtual card reader for a lot of things. Many shops don't have real tape anymore either. And often there are no physical printers, but you're often going to generate reports and distribute them probably in electronic format anymore. But so there's a virtual print function that you want to have, and VM's really good at that. So you'd have this set of real resources, that's the blue things, and Prism carves those up, lets the LPARs have access. In this case, Prism can allow multiple LPARs to share the same disk, for example, or tape. But then ZVM, like I said, can do much higher level virtualization with a lot more overcommit and control. This is a really old chart. I searched around for a current chart. This is a Z13. I mentioned earlier, one of the things that the microcode can do, Prism microcode, is to dynamically spare, and this is just a depiction of how that would occur on that class of machine. So if one of these cores fails, the LPAR microcode can actually dispatch that work on an available extra core somewhere. And this is a little bit of text about how that works. And it can happen across multiple drawers if you have a multiple drawer machine. That's really all I had to say. I just wanted to show you that, here's this swap button. So we've got, a failure up here. It's going to put it down in this other, but potentially the other drawer even. If something goes wrong, machine's going to take care of that for you. So I've mentioned different operating system names. These are the 5 primary operating systems. I didn't include KVM as a separate operating system because I really think it's a function that runs on top of Linux. Someone might argue with me and correct me later, and maybe I have to include it as a separate one. But primarily, these are the ones that we're interested in because we are. My experience is primarily ZVM. I put it at the top. A highly scalable virtualization hypervisor. These are definitions that came right off of the IBM sites. I didn't create these, or in the case of VSEN, it came 21st century. So highly scalable virtualization can run anything. ZVM, Linux, ZOS, ZTPF can all run as virtual machines. ZOS, highly scalable and secure and scalable operating system. This is the world's most mission critical applications. So you'll find this in all the large financial institutions, vast majority of the world's data, healthcare underneath the covers, even though they have some really pretty front ends now. Most of the back ends are still ZOS systems because of the security and scalability of those environments. You're talking about things there that have to, maybe not the 1 trillion web transactions per day, but hundreds of thousands of transactions. I've heard banks have those kinds of numbers in ATM transactions alone, and all of the interbusiness communications. So ZOS is a key user of mainframes. VSE, smaller scale, but serves as the same kind of hybrid data and then cloud environments. ZTPF is probably the highest transaction processing facility in the world. So it was designed for the airline control program. So if you ever reserve a flight, a lot of the times when you're going to those kiosks or the consoles that the attendants are using in airports, all of those clicks and clacks they do in order to schedule you, print your boarding passes, all that stuff. A lot of those are still ZTPF running. And Linux, most of us know Linux. It's the free open source, free in some terms, open source operating system, and it runs on everything from small wristwatches, etc., to the world's largest mainframe. Some of the largest workloads running on mainframes with huge databases are hosted by Linux. So all of those things, it's a huge infrastructure and a cooperative environment ecosystem on the IBM mainframes. So my summary chart, it's different because the hardware is different. It's a complex of processors working together. It is an integrated design. So we have everything from the hardware through the application environments. New processor designs enable agile feature development. That's one of those key ones in the Z17 was that data processing unit or the IO firmware processor. Virtualization is integral to the IBM Z hardware. So whether people know it or not, they're running virtualization in the form of Prism at a minimum, and hopefully they're running ZVM in addition to get higher scalability. And then the operating systems to handle all of those IT solutions that I mentioned on the previous chart. And that is everything. Appreciate your attendance. If you have questions, you've already heard from Sam. And with that, I can turn it back over to Sam.
All right, thank you, Rick. That was awesome. So now we're going to take a quick 10-minute break. I'm going to set a timer and we will see you back here in 10 minutes.